welcome to the 14th lecture. कल check कर लिया मैं 13th. Right. क्या किया last time? What did we do?
So, moving average for random harmonic.
Right. So the general theme was now looking at some random models or processes. Yeah.
Yes.
It's good to see them as models. Like as I said, in the deterministic math, you have so many models: logarithmic, quadratic, right, linear. So here, these are now going to be our models that we will try to use to say represent different random processes. Some situations may be well represented by a sum of random harmonics. Others may be well represented by moving average, others by autoregressive, then others by Brownian motion, Markov chains, all that. So basically we did random harmonics first only with one random variable, the amplitude. Then we added another random variable, the random phase uniformity. Yeah. What did that change in the characteristics of the random process? एक बहुत बड़ा change आया था, right? This seemingly small thing changed largely made it wide sense stationary. First case, it wasn't wide sense stationary, right? So and we drove those. Then we did a bit of moving average process, right? So where we saw that this is a kind of process which is made up of sum of weighted average of underlying random happenings. What was the condition of the underlying random things? They were independent. They had the same mean and variance, right? So we will see that later. We call this thing independent and identically distributed. We will see that again today. So we move on to the fourth example now here that I have, which is okay. So you have heard of Markov chains? Yes. So what is the whole theory of Markov, the guy? पता है कौन Russian mathematician? Yeah?
Yes.
So it seems this field seems to be more dominated by Russians, Kolmogorov, Markov, and then there will be others. So क्या है? What is the key idea that makes this field of Markov processes, Markov chains, or the Markov introduction in probability? Do you have idea? Markov property का सुना है? That's why I know. Yeah, right. So there is a very simple line that just starts this whole field basically. Yeah. So I will come to that, and with that we will also see the discrete time Markov chain today. So let's start with a sequence of random variables. Yeah. So today we are looking at discrete time Markov chain, at least starting with that. But I am not too interested in the single discrete time Markov chain. I want you to know also what is the question that starts all of this thing. Yeah. So consider a random sequence. Let's say a random variables. There is a sequence of random variables x, k. Yeah, and let's say they are like okay. Sometimes it helps to write like this. And there are assumptions here. Okay, this is a sequence of random variables. Each one of these is random. Beyond that, we haven't said anything yet. Yeah. Now let's start qualifying that. Assume that each xk is discrete in state. Okay. So it is a discrete state random variable. Yeah. What does that mean? इसकी जो values it can take are not continuous. They are a discrete set. So let's say we label those states S0, S1 or so on. Yeah. So we could label them. Each one has discrete states, and the states are labeled, let's say 0, 1, 2 and so on. We will call them state labels. Now each of these takes from the same set of states. Okay. For example, let's say each of these is coming from rolling a die. Okay. So is that a discrete state system? At least it has how many states? 6. Yeah. So if you said, okay, I have 6 states, S0, S1, S2, S3, S4, S5 and S6. What were the states? 1, 2, 3 for a dice. Yeah. 1, 2, 3, 4, 5, 6. Yeah. So
Why we start this?
1, 2, 3, 4, 5, 6, 8. One is a start. State not or state.
yeah. So basically state 0 is 1, 2, 3, 4, 5, 6. 6 states. Yes, for the dice. Why do we want to keep it like this? Because we want a general situation where it can have any number of discrete set of states, and they are just labeled. Yeah, we're generalizing here. Okay, so that's one condition. Now suppose for some reason it happens that this process, I have not put any condition on the distribution. Yes, I have not put any condition on their independence or anything yet. Yeah, only condition I have put is they are discrete state. Yes, and they take states from the same set. Okay, that's also important. So it's not like this is rolling a die and this is tossing a coin. Then they are both discrete state, but their state sets are now different. But here they have to be from the same set also. Right. Then if it happens that probability of xn, conditional probability of xn, given all the previous values, happens to be the same as probability of xn given just the last value, previous value, for all n. Okay. Then we say that this process has a Markovian property, so I'll describe that, but first look at this. What is it saying? Remember, this is not a case in general. We are saying, let's say it satisfies. Assume it satisfies, okay? In general, there is no need for processes to satisfy this thing. Assume it satisfies this condition. Now this condition is actually the crux of the whole Markov idea. So that's why I'm emphasizing here and stopping here. What I want is for you to see that Markov idea before I explain it. So what is this condition saying? You use all the concept we discussed about independence and conditional probabilities and all. So, क्या कहते हैं?
जितने से रैंडम वेरिएबल्स हमारे हमें मालूम हैं, नोन हैं, उनके बेस पर हमारे पास n की xn की डिस्ट्रीब्यूशन और जस्ट प्रीवियसली स्टेप वाले डिस्ट्रीब्यूशन हमारे पास सेम है.
Okay, so can you explain it in terms of its distribution? तो है in terms of knowledge or something. Conditional probability क्या होती है? What is this one saying? Probability of xn given information of the whole history. Yes, ये कह रहे. So yeah, the conditional probability. So if I tell you that the history was that all the previous values had taken these states. what state will this guy take now? Conditional based on the past, whole past. What is the right hand side saying?
Just before.
Just the last
Just
one.
one.
So what does that mean together? It's
Same.
it's same. Equal means same. What does that now? Can you say it in words? Start with knowledge of. I'll help you. Knowledge of the whole history. Yes.
The history doesn't change.
I say if all of this, if these are equal, do I need this knowledge? Only this guy was enough.
Yes.
Yes. So this is an assumption that the conditional probability of the current state, right? Knowledge of the whole history is same as having knowledge of just the last value. So what is it saying? The knowledge or the information that the whole history was going to give you is encompassed in the last value. Okay. Knowledge of the last value covers the whole knowledge in terms of statistics. Actual values आपको फिर भी नहीं पता चलेंगे इनकी, right? But we are not talking about actual values. But however, what is the probability that xn takes a certain state? If I give you the whole history, right, that is the information I input, the conditional probability you get, if that happens to be the same as saying that all the information is encompassed here. Yeah, that's why they are equal. That's the assumption. Okay.
We have no need to check all previous history. We can just.
Yes. So it's like this. I write it here. That is, knowing xn minus 1 alone gives the same information about xn as knowing all the past values, right? If a process has this property, okay, we call it Markovian. Okay, and this property is called the Markovian property. Such a process can be called Markovian, or it's sometimes also called memoryless process, memoryless property. Okay, and this simple line, okay, forms the foundation of the whole Markovian field. Okay, it all starts here. Notice something like this we haven't done before. We have talked about they are uniformly distributed, they are completely independent, they are correlated so much this, but this is something very new, yeah, and seemingly very odd. क्या करना है इसका? Well, this leads to random walk, Brownian motion, the whole field of Markovian chains. Yeah, और Markov chains की importance cannot be overstated. Extremely important field. पूरी किताबें हैं, books, पूरे course होते हैं. Yeah. So this kind of Markov chain, that kind of, then people went crazy with the Markov chains.
So there are lots of philosophical discussion about this Markov process, not
Yes.
about mathematical.
Yeah. So again, since it's important, we'll of course not come back to this too many times. What it's saying is that if there is a process, right, that has a discrete set of states, and it's the variables, the random variables in that process have the Markovian property, which means that the probability of any xn at given time, or if you want to take the next one, then previous, what state it takes, that probability, whatever information the whole history had to give you, is already covered in just the last one. Okay, then we call it a Markovian process, and that is a Markov property. Now this leads to Markov chains and so on. Now Markov, the idea is not limited here. This is where it starts, and this is actually a first order Markov chain. Okay, there can be a second order Markov chain. Can you guess what that would be like? First order, second order. क्या होगा? क्या चीज़ एक से दो हो जाएगी?
Sir, what exactly?
Yes. Then there is a second order Markov chain which says in those chains or in those processes this equation looks like this. There is a comma xn minus 2. So the whole history is encompassed in last two.
Last two, yes.
In the nth order Markov chain, the whole history is covered in the last n or k or whatever order you want, right? So then that expands the whole idea. फिर बहुत बड़ा हो जाता है, right? Then there will be processes that will have first order Markov property. There will be processes that will have second order Markov, third order, fourth order, and so on. Yeah, but the whole thing starts here. Now, this thing finds application in physics, economy, operation research, biology, machine learning, a lot of machine learning. Yeah, and literature. Okay, आपने philosophy भी बताया लेकिन वो exactly इस time but discussion. So literature, where does literature come in? Markov himself applied this property to predict what next letter will be in a. There is a huge large Russian poem, Eugene Onegin. Pushkin नाम सुना शायद, very famous writer.
Right.
Markov applied to he has a very long poem. Usually these are called epic, body stories, yeah, poems. And he applied these properties, and he was with high probability able to, or with high accuracy able to predict. See, अगर ये there's one letter is here, then what's the probability that the next letter will be this one? Yeah, or letters. The letters that appear, do they satisfy this? There is a finite state has one की finite alphabet होती है, right? So Russian की जो भी है वो finite states थी. So he was predicting what's the state. Is it the next letter and S? What's the probability? Given that the last letter or the last two letters, depending on what order he applied, right? He also tested what is the probability of two vowels coming together. Pushkin's poem. Yeah. So the beauty of the Markov chain is that you can take a lot of data, train or get the kind of train the chain in a way, get transition probabilities, and then predict the next transition. Okay, so it's amazing, eh? Right. So I will not write here the let's say nth order, but I already told you this is first order. If we want order h, that means xn minus 1, xn minus 2, xn minus h. Last h values cover all the information you need, or let's say not need, but all the information that you would have had from the whole history is covered in those values as far as probability or conditional probability is concerned. Right? Okay, so second order is here. Now we often visualize Markov chains. Markov chains जब आप सुनते हैं तो I don't know अगर आपने कभी at any stage you have gone through Markov chains, वो figures आती हैं में जो chain actually ये chain क्यों कहते हैं इसको? Now we will see the chain. Yeah? वो transition diagrams बनती है ना उसमें. So let's see, we often visualize Markov chains through state transition diagrams. Okay, so let's say I have a Markov process that has three states. So what am I saying? I'm saying these axes now can take only three states. Yeah, I will label them as 0, S1, S2. Because of this label, I don't have to care about what the actual value is. Yeah. This general label I took. So, so this process has three states: S0, S1, and S2. Okay. So these, I just want to show you for one Markov chain, then you will get the general idea. Yeah. So I'm going a bit slow, but then later you can just make as many as you like. Right, so these circles represent the states.
States.
Okay. Now let's say I tell you that the probability xn equals 1 given xn minus 1 equals 0. Now in writing Markov chains we often skip this s. When we write 0 we are saying s0. Okay. When we write 1 we are talking about s1. Okay. So normally it's like done, but you could do it. You could actually write s1 here also. It's fine. We're talking about s0. So the probability that first let me write it equals 1, yeah. And probability xn equals 1 given xn minus 1 equals 1 is 1 by 4. Okay, so I'm assuming a first order Markov chain and just going to draw its diagram here. So can you tell me what does this mean for our case now? Read it out, like क्या represent करता है?
Probability is one given that is not equal.
So probability that the next state will be S1 given that the last state was S0 is what? What does that mean? So whenever you find yourself in state S0, where will you go next? Do you go to
Strongly
S1?
S1.
Always go to S1. Yes, with probability 1. So this is called transition. Okay. So what this is saying is, since this is transition from 0, if you are the last step you were state you were in was S0, then with probability 1 you will go to state S1. This is what it's saying, right? And we often write these, अब वो आपको familiar सा मिल जाएगा जो state transition probabilities हम लिखते हैं. In the field of Markov chains, this is also very well known and we use notation P01. Probability of going from state 0 to state 1. This is this thing, and in our case I just put a value here, 1. Yeah. So what about this one? What does it say? Can you read it out now?
S1 पर जाने की
So what does it say really? Your process was in what state? Where was it? Here. Start कहाँ से होना है? यहाँ से, yeah? It's in state 1. What's the probability that it stays in state 1? तो stay का मतलब क्या होगा? What is that probability? 1 by 4. Okay, I just these values I'm just writing. We haven't derived from anywhere. Just could be anything. I'm just trying to show you states, state transitions, and these transition probabilities. मैं आपको symbols और जो vocabulary है ना वो बता रहा हूँ, right? So how do we write this one? How do we define this thing? P 1 P11. Yeah, probability of going from state 1 to 1, meaning staying back in state 1. This creates such beautiful ways of representing how things will end up. You know, let's say if this was 1, let's say, you know, then if you simulate this thing or run this thing, you can already guess that as soon as the process reaches state 1, it will get stuck. Let's say this was 1. Yeah. So what is it saying? The probability of going from state 1 to 1 is, so let's say you start the process here, it jumps, goes somewhere, but as soon as it reaches here, it gets stuck, because if it was 1, yeah, so this node will behave as a sinkhole. Yeah, so some nodes behave as sources, some behave as sinkhole. Kitna wo attract, this can create such dynamic understanding of how the states will evolve. Yeah, so in this case, this transition seems very powerful. Yeah, so a lot of this will happen, and then I'm just going to write some values of. Similarly, we could have others. Yeah, so the probability of going to state from state 1 to state 0, let's say it's 1 by 4 also. Yeah. Just to explain or let you see these different transitions, and the probability of staying back in this is 1 by 2. If a probability is 0, we don't draw that line. Okay, so if I haven't drawn S0 to S0, it means that is actually 0. We only draw the non-zero ones, वरना तो बहुत कुछ draw करना पड़ेगा. Similarly here, half. Okay, so the reason I have shown you this is I wanted to cover the state transition diagrams, different elements. So what are the elements? It starts with the states, yes, and then you have to assign all the possible transition probabilities. How you find them, we haven't discussed that yet. Yeah, abhi sirf humne symbols and the terms and those we have discussed, and I am not going into this detail at the moment. I just gave you an idea, but there is a lot of information even within these states. You can already start seeing, okay, this process will mostly, let's say, end up in state 1 or state depending on the total probabilities, right? So if it starts in state 0, yeah, let's say, where does it go?
State 1.
Will go, because it is 1. So 1. Now where does it go next? It's stuck. Yeah.
Stuck भी हो सकता है, state 2 पे भी जा सकता है.
Sorry, in this case, yeah, sorry, it wasn't 1. So it's 1 by 4 of staying here, but then going to S2 is this thing. Yeah. So similarly, you can have others like that. Yeah. If there was a 1, then this will be getting stuck more often. So if it starts in state 1, right?
Yes, sir.
What are the chances that at some point it will go to, or now at least go to state 0? 1 by 4. Yeah, and similarly 1 by 4 chances that it will come back. Yes, and half and half chances, sorry, only half chance here that it will go to state 2, right? And I won't go into the details, but you can already guess that the arrows going out of it have to sum to 1, right? एक ही करना, it has to do one of these. Yeah, if you are in state 1, you will either go to state 0 or state 1 or go to state 2. और तो state नहीं है ना. So the arrows going out of it, any node have to sum to 1, and then there are many other discussions and results that you can derive. Okay, so there are whole chapters on Markov chains, books, courses. We won't do too much of it in this course because we have to cover several different things. What we will do is do the most relevant part of Markov chain, which is random walk. Random walk is actually a first order Markov chain. Okay, so that's why, and it's good to have this in mind. At some stage, if you want to read on your own Markov chains, if you want to use them with the information I've already given you, you can start reading on this. Yeah, take another course on it, read it on your own, depending on what you need. Right. So lot of the literature on Markov chains discusses how to identify the order, how to decide the transition probabilities, and after that how to make different decisions. What is the probability that 80% of the time it ends up in state 1, ends up in state 2, like that, yeah, and that helps you with decision making. So if you have simulated your situation with the help of Markov chain and you realize that your system spends 90% of its time in state 2, okay, then whatever design you are making should focus mainly on state 2. State 2 could be some special mixture of temperature and pressure in a, let's say, in a chemical experiment or something, yeah. So there's a lot of information that you can extract from the chains. अभी जो मैंने बताया था ना, Pushkin, he applied, Markov applied to Pushkin's poem. See, he was predicting what's the probability of vowel going into another vowel, what's the probability of letter S coming after letter A, all those things based on the whole data of the poem, right? So it helps a lot with predictions and analysis, but we go to now its special realization that we are interested in, that is a random walk. Random walk, so now idea to है, yeah. So I've already mentioned it's actually a Markov chain, and it is this random walk that will lead us to our friend Brownian motion. Okay, so that's why I'm going this way. Okay, so we are connecting Markov, random walk, and then going to Brownian motion. Brownian motion is going to be a limiting case of this guy. When things become infinitesimal, we'll see that. You will get a limiting equation, and that will be the Brownian motion. Okay. So random walk. Okay. वैसे तो random walk love से ही समझ आ जाती है, like you're taking steps, yeah. But in mathematics we are writing it as random walk, and it is in fact a Markov chain, because we will see that it satisfies the Markovian property. Okay, that's why it's a Markov chain. Yeah. But let's define the random walk. Let's set up the experiment. So you consider a discrete time, discrete state random process. Okay, we consider a discrete time, discrete state random process where at each step you either go up one step or you go down one step. That's all. These are the only two possibilities. Okay, so you go at each step, you either go up, so +1 with probability small p, some probability, 0.5, 0.3, whatever, or you go down one step, that is you deduct 1 from your value. So let's say if you are your value of x was xn minus 1 was 10, then going down one step means that if value counted down by 1, it became 9. Yeah, like that. And this has to happen since you are only allowed two possibilities. You can already tell me what the probability of this should be. You can either go up one step or go, no third option. Yeah. Then if the probability of going up is p, 1 minus p, yeah.
Yes.
और कुछ नहीं हो सकता, वरना गलत हो जाएगा. Then you're missing a state or something. Yeah. So firstly, notice that this is a two-state system. State 1 is, yeah. So
It's not
it's not a two-state system. It has many states, but they are discrete because you are going up or down. So I'm going to plot it to show you.
We stick it to one state, then it become bundle.
Yeah, it is. I think I will take those words back. It is not a two state. It is only allowed two transitions. Yeah, states you will see are actually infinite states, but they are discrete. That is correct. We will see that. But there is an additional assumption that needs to be satisfied, and that assumption is that the choice between +1 and -1 is independent of the past choices. Okay, so if you choose +1 at any state or you choose -1, this is independent of whatever you chose before. That is important. Okay, so basically choice between +1 -1 is independent of past decisions. तो अगर आपने पिछली 6 दफ़ा last 6 times you took step down, that does not tell you anything about what you will do next one. Yeah. Okay. So then how can we write the current state of the system? Yeah, the state Sn. What can we write about it? So let's see. Let's draw it and then we see. This is a discrete time also, right? Okay. Let's say, of course, initial conditions come in, but we just want to draw one realization to understand the scenario. Yeah. So let's say you were here at, I will start at 1. So you were at 1. Yeah. You are in this state, state 1. At this point, what can you do? You can either go down or go up. You go up with probability P, go -1, that will bring you to a 0 with probability 1 minus P. Let's say we actually happen to go up, and you can go up by +1 only. Yeah, so you will be at 2. So now you, of course, since it's a discrete, the only transition will happen now here, not in between. Yeah. So let's say now I've drawn this, so it doesn't matter whatever we draw anyway. But let's say you again go up. 3, and you are here. Next time maybe. Next time maybe you come down one step. And now I'll just draw a few things. I like to have the same figures. So actually not. Here also you go up and like that. Yeah, and come down. And of course you can come here also. Yeah, हो सकता है ना? Just came close to coming here. Yeah. So right. Now let's call this thing, this point, let's call this its current state, Sn. These are the states it can take, agreed or not? And those are infinite. Are discrete numbers, yeah? Are integers in this case, yeah? Right. This is the current state, whatever it is, and this was its last state. Agreed? Yeah. Okay. So how can I relate these two states? Yeah. Let's see if I have defined it here.
Sir, here we have discrete process and discrete random variable. We are saying that, and it's discrete in sense of integers, not in the sense of points.
No, this is discrete time and discrete state. Yeah. So state means it can only take these states. Yeah. Not 1.5, 2.5. And time means that the transitions can happen only at these points. Yeah. Okay. So then, how can we write Sn in terms of Sn minus 1? Can you think of a way to write
Sn given
Sn in terms of Sn minus 1 something here. So let me write it for you. Let's start with this thing. Let's say Sn, if you will agree, is a collection of all the steps that you took, isn't it? So let's say the first step, the first or the starting condition was x1. Yeah, you were in state S1, and then whatever next one you took. Yeah. So what are the possible values of these x's? Each step, what are they? Each of these x's takes value plus 1 or minus 1. They are finite state. Yeah. Each of these x's takes either value plus 1 or minus 1. What's the probability that any given x takes plus 1? It's small p. Yeah. And what's the probability that any of these has value minus 1 is 1 minus small p. Yeah. So can I say that it's actually the current state is actually a sum of all that happened until now? Agreed or no?
Yes.
Yeah. So then x3 up to xn. Okay, so n transitions led you to Sn. Each of those transitions follows this thing, and we are already saying that they are independent. So what does that mean in terms of axes? All the axes are independent, right? So now each xk is a random variable, right? Yeah. Yeah. So each xk is a random variable that has how many possible values?
1 and minus 1.
2 possible values, right? And what are the probabilities of those? P and
1 minus 2.
1 minus p. Other than that, we have no assumption on the distribution or anything here. Yeah. So p and 1 minus p plus 1 and minus 1. These are x's, not s. Yeah. Markov chain or the random walk is not x's. It's actually this guy.
Yes.
Okay. X is just one transition each time. The overall state you are in, that process is the Markov chain, and it is the random walk. Then we will show now why it is Markov chain. We haven't shown that yet. We are just developing this thing. But what happens here? Now can I write Sn in terms of Sn minus 1 using this?
Yes,
How shall I write it?
X naught x1 becomes x naught and x2 becomes x1.
No, we'll shift this up to xn minus 1. We will consider it to sn minus 1 and we'll shift on the right side.
So what should I put here? Just tell me that.
xn.
Xn. Right?
Yes.
Agreed? If Sn is sum of n transitions, then Sn minus 1 is sum of the n minus 1 transitions. So वो जो n minus 1 यहाँ है, they are actually representing Sn minus 1. So this equation is there. Okay? So it simplifies. Yeah? Now, let's see. This thing, of course, has the we will come to that. Let's first we have already written 1 minus p, so we don't need to write that. And of course all the x's are what are they? I forgot to write this. All are independent, right? This was in the setup of our experiment. So this kind of processes or random variables, sorry, that are independent and they come from the same distribution are called independent identically distributed, IID. This short form, sometimes written like this, is heavily used in the field of random processes estimation theory. They just write the assumption is Gaussian IID. So Gaussian, you know how they're, but IID says They can be uniform IID. Distribution can be any. What this says is, what is it saying? That they have these two properties. First property, they are all independent of each other, I. Second property, whatever distribution they come from is the same for all of them. Sometimes students confuse IID with Gaussian. It's not saying anything about the distribution. It's only saying whatever distribution one x comes from, the other x comes from the very same distribution, okay, with the same mean and variance, okay. So and everything same. So this is called independent identically distributed. Identical, you know, similar, yeah. So they are identically distributed, IID. So xk's are IID. This is not critical in our development, but because this term is very important in this field, so please keep it in mind what it represents. Okay. So now tell me, does Sn, this guy, satisfy Markovian property, and of what order?
Sir, first one I think
Yeah. So
because we take Sn and Sn minus 1.
let's check it then, huh? Yeah, you're right, and of course I think I mentioned it also. So now what we show will make it Markov process. So far we have developed it as a random walk, yeah, with two states, two transitions possible, +1, -1. Okay. So probability Sn given Sn minus 1 and so on is the same as probability Sn given Sn minus 1. Okay?
Yes.
Is it true or not? In this case, does it hold?
Always no.
If you know where you are now, yeah, where you are now, you don't need to know the whole history to tell me the chances of going here or here. The chances are P and 1 minus P, right? So this setup naturally ends up becoming a Markov chain of the first order. The whole history becomes useless or redundant, at least, in talking about what the next only. See, this guy actually has this whole history. वहीं से तो पहुंचे हैं ना यहाँ तक. The whole history got you to this state, right? So this state covers, statistically, it covers all the information that you need from the.
Similarly, tossing a coin, sir, it's a random walk. Where 10 times tossing a coin, we have no need to previous data. Just you could say in that sense.
Yes. So tossing a coin, and you want to say what's the next toss will show you, right? So
10 times toss will show you. For the 10, we would toss 10 times. First time, second time. Then we are interested in, okay, what is the probability the head will come. So it will not
But
depend
in
on
that
previous
case,
one.
you know, probability that the kth toss gave something, given the k minus 1, the toss is actually probability of xk. Yeah, even that is useless. वो जो आप तारे हैं, जो है completely independent.
Yes.
Yeah, so that doesn't really start with the first order. I don't know if there is a zero order Markov. You see the difference. In that case, you don't even need the last one. वो तो सारे independent है ना, like the x's here. Yeah, Markov starts with saying you do need the last one, but you don't need any others. At least in the first order Markov chain.
Sir,
जी.
sir,
So-
here Sn minus 1 covers all the previous information. So when we go in second order Markovian chain, so
You
we
will need
write Sn minus 1
Sn
and
minus 2.
Sn minus 2
Yeah,
also.
yeah.
But Sn minus 1 covers all the information, why we mention Sn minus 2.
Yeah. So there will be in this setup, this is first order. You cannot just put second order here. Yeah. But there are setups we can change this scenario, and then you will have, for example, it will be based on Sn equals Sn minus 1 plus Sn minus 2 plus Xn. Then it will become like that. Okay. So if you find, just Google an example of a second order Markov chain. We are not saying that we will just put one thing here and it will suddenly become a. Like, this scenario is first order Markov chain. इसमें वाकई नहीं चाहिए वो. If you have a situation where this last one covers everything else, this is first order. You cannot say, okay, now I can bring the second one and make it second. Okay, so that is a different scenario. उसके फिर अपने realizations है कि second order Markov chain क्या होंगी real examples में. So just Google it, you will find several. But the random walk I'm talking about is first order Markov chain, and this is what it covers. So now I want you to write the first help me with this thing. What's the probability Sn equals I plus 1 given that Sn minus 1 was I? G. Where I is a set of integers. From I is in the set of integers. Yeah. So simple as well. ये बतानी है probability.
2p minus 1. Two p minus 1 p है दूसरी minus p है sir 1 पे.
So what is I?
I is a
Integer.
Integer.
Just put some integer here. कोई बोले? 1. Okay.
1.
Then what is this?
2.
2. What I now read it. What is it saying? Probability that the next state will be 2 given that the previous state was 1.
1.
How do you get from 1 to 2?
In random walk
Yeah, in this situation.
by transition with the probability 1 or 1 minus p. So
अभी आपने कौन सी ट्रांजिशन किया? ऊपर को किया, नीचे को किया? Going from I to I plus 1, is it?
ऊपर हो गया sir.
उसकी क्या चांसेस थे?
p.
बस ये.
मैंने दोनों को कैलकुलेट करा था ऊपर जाने के लिए 1p into 1.
नहीं लिखा तो नहीं हुआ ना. Right? So then of course you know what I'm going to ask next. ये क्या कह रहा है?
ये 1 minus p हो गया sir.
Yeah, probability of going up one step, probability of going down one step. Yeah. Why am I writing like this? This is the state thing. Yeah. P. This is we will see that. Yeah. So this is 1 minus p. Okay. So can you draw the chain for this? Markov chain draw कर सकते हैं? तो मैं draw नहीं की थी पिछली जगह कुछ. इस केस के लिए draw करें. You can write the states as the numbers. You can skip S0, S1. You can write the states as क्या possible states हैं इसकी? All integers. नहीं Markov chain की.
1, 2, 3, 4 up to n integers.
नहीं. Overall, this chain can have any integer. Right? You could be stepping here, then stepping down, then going up, down, one step. Yeah. So you could be in state 1, 2, 3, 4, 5, 6, or minus 1, minus 2, or at 0. Yeah. So let's write a few states. Let's say draw 4 or 5 circles. Write in them minus 1, 0, 1, 2, 3, and then dot dot dot. Those will be your states. Yeah. So I think Ali has drawn it already. हो गई? यही है ना? मजे की बनती है.
Yes sir.
Yeah. So that is the
Simple.
simple है ना. that is the chain you get.
S1 to S1 से फिर हमारे पास जीरो ही होगा इस केस में, क्योंकि हमने तो मूव करना है ना आगे कंटिन्यूसली।
हाँ, इसमें जीरो है, बिल्कुल जीरो है, बिल्कुल अलाउड नहीं है। The way we set it up, it's not allowed. So it's actually as you have already drawn. So you go, take a step up by P and take a step down by 1 minus P. अब just to just an intuitive answer, let's say P is 0.8. Okay, P is 0.8. What would most realizations of this process look like? Overall, is it something mostly going up or mostly going down? If P is 0.8.
Mostly going up with a higher probability.
Yes. So you can already check, okay, this kind of process will mostly be, sorry, it's not continuous, so you have to draw discrete, you know. But some realizations will still go down a bit, yeah. But mostly, this is the probabilities, yeah. Mostly it will be a process that will be increasing, yeah. So you can already try. I'm just giving you a very quick glimpse of the power of the Markov chains. बहुत इसके अंदर वो होता है, lot of information, इसीलिए तो that's why there are whole books and courses and fields on this, because there are so many things you can extract from the concept of this chain. Once you make a chain, there's so much literature on, okay, what is this, what is that, what are this, what transitions are stable, what transitions are unstable, what transitions are most likely, what's the overall behavior. So much you can find. Okay. So as I already mentioned, this thing that we have drawn and worked with is called a random walk. Okay, so random walk फिर क्या है? Random walk is a Markov chain firstly, and we write the random walk as Sn, yeah, and you can define the random walk in two ways. Okay, as I started with all that xn and all that, or just come here. Yeah, so if you have Sn, this is a random sequence, Sk, let's say. This random sequence is a random walk if it has this thing. Yeah, what is that? The probability that it goes up is P and it goes down is 1 minus P, and the information about the axis being independent and all that is already covered here. उसी की वजह से ये आता है.
Mostly हमारे पास prediction model में हमारे पास इस्तेमाल होती है random walk के लिए.
Yeah, prediction, predictive models are the most common, I think. Yeah. Right, so before we end for today, just a quick question that you can try to answer. Is it white sand stationary? Dani to take it. Is this first order Markov chain, the one we just defined, the random walk, is it a white sand stationary process or not? What do you think?
Its expectation is not dependent on time.
Mm-hmm. So what is the expected value of Sn?
Zero.
Sure. It's something that can help you. I write that.
P होगी
Remember Sn, we were also able to write it as x1, x2 up to xn. Maybe this will help you. Now find the expected value of Sn.
NP
N P. It's NP minus Q. You can try to solve it at home.
1 minus P is
P Q is 1 minus P. So
Yes,
we could write it if you want to write just in P. Let me write that also. NP minus Q, where Q is 1 minus P. So it becomes P minus 1 plus P. So it's N 2P minus 1. ये अब बताएं means constant है really. So the mean of the state at time n has end. So state 1 ka this S1 will have 1 times this thing. S2 will have 2 times. तो change हो रहा है. Right? So and I see we have few more minutes. Let me just quickly cover this or tell you this next thing, which is how this leads to our friend the Brownian motion. So what the idea is, remember this one, we just have drawn this random walk thing. Okay, not allowed. So ऐसा कुछ था ना जो अभी हमने one realization of the random walk. So Brownian motion comes just from one simple thing, saying okay, what if we allow this thing to be continuous and this thing to be continuous? Okay, what does that mean? Transition can happen anytime. And by what amount? Previously we limited it to plus 1, minus 1. And it can happen, let's say by, actually we want to have it that the transition size, we're not going to assign it any value. Say it's going to be infinitesimally small. Okay, so the transition, let's say this transition, previously what was it, plus 1 or minus 1? Let's say we call this transition delta, and we say what happens as delta approaches 0, okay, and what happens as this was our transition time, this approaches 0. As n approaches, we will let n approach infinity. Okay.
Step size of particle small, like you spray a perfume, then its spreadness.
Yeah. So the step size is going to be the step here is going to be small, and the transitions can happen very fast. Okay, very quickly. We want to allow that. How would this look, by the way? कैसा लगेगा ये? If these are allowed.
That's a kind of a random thing, very थोड़ा शॉर्ट से इस तरीके से
हाँ हाँ शॉर्ट से होंगे ना.
लाइन
So let's say I start at the same point,
यस
है ना?
ECG टाइप इस वन
Yeah, this is actually your 2D Brownian motion. Okay, और the diffusion process वगैरह ना वो that depends on the overall probabilities of the states or those things. Yeah. So this thing now, by allowing this, this becomes T and this becomes, पहले क्या था ये? This was S. So any state at any given time was Sn. Yeah. Now this, since this guy can end up in any value, continuous हो गई. So this is Wt. Similarly, this here was n, like or h 1 2 3 4 discrete tha. Now it becomes continuous, and this thing has become a Brownian motion. There is one assumption that for mathematical sake we need to have on these two guys, which is that their ratio should approach a fixed value alpha. Okay, I have skipped that. Conceptually this is enough, but if you don't force this, what will happen? They can collapse to degenerate. Okay, वो भी जीरो हो जाए, ये भी जीरो हो जाए, अगर दोनों अलाउ कर दें आप, तो इधर से आप शुरू करें बस इधर ही नाचते रहें, डीजेनरेट हो जाएगा ना. डीजेनरेट समझते हैं when collapse हो जाता है फंक्शन. या so to avoid degeneracy or to avoid that trivial case we require that इसके पीछे पीछे फिर description है, you can check in the Kobayashi I think and also in Lindgren, they may have references there, but for some alpha greater than 0, this as limit delta goes to 0 and h goes to 0 with this condition. Okay, with this condition, so I'll write it now here. Let's write the whole thing then to get the mathematics done. Limit h goes to 0, delta goes to 0, n goes to infinity, so we want to allow it to happen for some time. Yeah. As this limit occurs, Sn becomes Wt with t equals nh and delta square by h equals alpha, where alpha is greater than 0, and where what would be xi is v, by the way. Now remember x is, we had this Sn equals Sn minus 1 plus x, and remember this guy?
Yes.
Yeah. So previously in the random walk, what was it? Plus 1 minus 1 with probability p and 1 minus v. In this case, I need space here. So in this case, xi are plus delta or minus delta with probability half and minus, sorry, half and half. Okay, so and then Sn will become a sum of so many of these, which will be infinitesimally small values, being positive or negative with equal probability. In this particular case of Wiener, you could say, okay, I don't want this to be equal probability, then you get something else. So but here this is what we have, and this is called the Brownian motion, this guy, and it has another name. So Brownian motion, and it's also called Wiener process. That's why the W is here. Yeah, it's also called the Wiener process, and we have already established that this is a limiting case of what? Of random walk, which was a case of Markov chain first order. Yes? So much.
Markov chain
Yeah.
is a huge guy
Yeah.
in a specialist case.
Yeah, उसका एक first order special case random walk, then the limiting case of random walk is the Brownian motion or the this guy. And if you thought we were done here, I'll just write the last thing, not new equations, but continuing in this thing, okay. The Brownian motion is a special case of continuous time, continuous state Markov processes called diffusion processes. Diffusion processes. Within those, diffusion processes are a broad class of continuous state, continuous time Markov processes. Okay, and within them there is this guy, the Wiener process or the Brownian motion. Okay, and finally, to top thing up, WT is Gaussian. I'm not proving it right now, we'll see if there is time. But actually the Wiener process is Gaussian. So that brings in one more thing. So a lot of statistics here. Yeah?
Suddenly when we spray then it's high, then it's
Yeah. Okay. So there is a general class of continuous state, continuous time Markov processes called diffusion processes, and within the diffusion processes there is the Wiener process which follows these. If you change these, you get other diffusion process. आपको मैंने कहा ना कि you don't have to have equal probabilities. As soon as you start playing with different things here, you start getting other cases of diffusion processes which are more generalized compared to the Wiener process. Yeah, this guy is the Gaussian Brownian motion. And again, where did this come from? This guy, it came from random walk. Putting limits here, right? Limiting case of random walk, and random walk was discrete state, discrete time. So discrete say, let's take the arrow there. Discrete say you're going to, ऐसे ही जाते हैं ना, पहली दफा जब कैलकुलस पढ़ते हैं क्या पढ़ते हैं? Limits, right? Limiting cases. So from discrete you put the limiting case, you get into this region which is, of course, makes sense, going from discrete of everything to continuous of everything. This thing is one field, this is another huge field. Yeah. So I think that covers our like 7 of our processes. Next time we go into point and counting processes. There we will see renewal, Poisson, वो फिर एक और दुनिया है. Yeah, and we will see if there are relations between these or not. Yeah, I've written here. In fact, a Poisson process is a continuous time Markov chain. Okay, so we are not done yet. Okay, so they're all linked.
it's a numberless process, not a Python.
Yes.